Hi, my name is Dane, and for my Capstone project, I've chosen to build an electronic instrument. I'll play a demo of the instrument first, and then explain the build process and why I chose this as my project. I chose this project as my capstone because I have an interest in music and retro instruments, including one instrument in particular that has piqued my interest for quite some time. It's called the Omnichord, which was a synth with a touch-sensitive pad for playing chords. Suzuki, the company behind the Omnichord, made a multitude of different models being produced until 1996. Since then, the instrument has become a fairly sought-after piece of music gear because of its unique sound and interface. With second-hand Omnichord models selling for upwards of $900. Unfortunately for most people, myself included, that's a bit too expensive to spend on an instrument that you can rarely find parts for and is prone to malfunctioning due to age. So I decided to design and build my own version with more modern features while still maintaining the same unique interface and retro appeal. To get started, I made a quick visual prototype to get some ideas of what I generally wanted the device to look like. I knew I wanted 3 rows of keys with some control buttons and to have the touchpad on the right, but I wanted to get a better idea of how everything would look as a reference for when I designed the case. This was the design that I landed on. Now, before I could start the final design, I wanted to make a small-scale prototype to learn a bit more about electronics before committing to ordering a custom PCB, so I bought a cheap electronics kit online to make a prototype. From this kit, I used a breadboard, a microcontroller, some wires, and buttons. This is what I ended up with. It has 3 buttons that connect to my computer to play chords, and even though it's pretty simple, this prototype helped me understand how to work with microcontrollers, which is a pretty large part of the full project, and really helped me. My next order of business was to begin designing a PCB for the electronic parts to fit onto. I used a design software called KiCad, which is specifically made for PCB design. And after watching this video on how to design a mechanical keyboard PCB, I started making the circuit. After a few days of learning the software, I had a design that I felt was ready to be ordered through a PCB manufacturer. Unfortunately, soon after it had arrived, I began running into issues with the touch sensor that I had been using for the project. The issue was that when I was using the touch sensor on a breadboard, it would connect and work fine, but when it was soldered onto the PCB, it would give glitchy, inconsistent results and sometimes not even power on at all. I can't stress just how long I spent troubleshooting trying to resolve this issue. I tried everything. I changed my code, didn't work. I bought a new touch sensor, it didn't work. I even tried a different microcontroller and no luck. This was easily the most time-consuming and frustrating part of the project. But after some investigating, I caught a tiny detail that ended up being the sole reason I was having these issues. When designing the PCB, I had used something called a footprint, which is basically a stencil that tells the software where it should place certain holes on the PCB so other electronics can be mounted onto it. I was using a footprint for a touch sensor made by a company called Adafruit. However, I was unaware that at some point they had updated the design of their sensor and rearranged some of the functions of the pins. So even though it looked identical to the old design, it could not be connected in the same way, and I guess the website I got the footprint from hadn't updated their design on that chip yet. Fortunately, the actual keyboard part of it had worked just fine from the start, so that part of the design didn't have to change. And since I knew I was going to have to reorder a new set of PCBs, I decided to make some improvements to the design before placing another order. I watched a bunch of YouTube videos on PCB design and fixed some of the smaller issues as well as the main issue from before. The biggest improvement was actually the placement of the touch sensor, which made it so that there was less interference because the traces were shorter and also reduced the overall size of the PCB. I also implemented something called via stitching, which is basically just covering the area around the wires connected to the touch sensor with small holes that ground it to the copper layer of the PCB, making something kind of like a shield around them, so any interference from other components can't mess with the reading of the touch sensor. I chose each part pretty carefully to make sure it had all the functionality I wanted while still being cost effective. For the microcontroller, I chose an Arduino Leonardo because it has a lot of pin inputs for keys, and I can use USB Midi, which is just how it'll send the notes to my computer. For the touch sensor, I chose an Adafruit MPR121 because it's pretty simple to connect and read from a microcontroller, and it has 12 touch inputs. I chose to use silent mechanical keyboard keys because they're cost effective and don't make a whole lot of noise when you're playing the instrument. And it also gives it a bit more retro appeal, kind of like an analog synth. Then for those keys to function, I used some 1N4148 diodes because they're inexpensive and are often used in keyboards for their fast response times. And that's pretty much it. It's just 4 components. So with my new PCB, I began soldering everything together. First, I soldered the touch sensor and the microcontroller on to test it out, and after a few minutes of uploading code, it worked. I played around with it for some time to make sure everything was working well before continuing on with the rest of the build. Now, all that's left to build is a case to house the electronics. The biggest problem to solve is making a case that can be printed in separate pieces. Since my printer can't print anything larger than 220mm in all axes, it has to be printed in multiple smaller pieces and then assembled afterwards. I went with a simple dowel that bridges the 3 parts, and then the top plate has screw holes that connects them all together. It's simple to assemble and about as sturdy as you can get from a 3D printed part. Now, with all my parts together, I assembled the instrument. After the main components were together, I applied some vinyl decals and put the keycaps on. And with this final keycap, the build is complete. The instrument is surprisingly diverse in the kinds of music you can make with it. Because it's a Midi instrument, you can make it sound like anything you want. It can sound like the original omnichord. It can sound like a stringed instrument. Or even a cat keyboard.
Meow. Meow.
And now, since it's done, I can show off a demo of all of its functions. When you press a chord button, the strum pad on the side will automatically sync to those notes and play them in ascending order. When you first turn the device on, it'll be in mode 1, which means that the chords have their own octaves and the strum pad just follows along with that octave. This makes it good for playing along with songs that aren't originally made for the omnichord. By pressing this button, it'll hold the notes in the chord when you press a button. This makes it good for playing along, and you don't actually have to hold the buttons while playing. These 2 arrows control octave and volume, so pressing it up will increase the octave, and pressing it down will decrease the octave. And this is the same for the volume, which you can change to volume select by pressing this once, and it'll change the volume control. Now by holding this button for 3 seconds, it'll turn it into mode 2. This mode makes it so that the strum pad plays 2 octaves higher than the chord buttons. This is good for imitating the exact functions of the original omnichord because that's how it would work at the time due to hardware limitations. So if you're playing a song that was originally made for an omnichord, this is perfect for that. As well as that, the chords are all playing in the same octave range. By pressing this for another 3 seconds, it'll be in the final mode, which is piano mode, and it's basically just what it sounds. It's a normal piano. And it's indicated by the blue and green buttons in the arrangement of a piano. And at this mode, the strum pad does not work. Now by holding it for another 3 seconds, it'll go back into mode 1, and I'll play, I guess, a demo song to show off the instrument. This project taught me a lot about 3D design, electronics, and manufacturing, and opens up a lot of doors in terms of job opportunities, with troubleshooting and critical thinking skills being very valuable in those fields. I also want to thank my mentor, Luis Castillo, for helping me troubleshoot some of the issues I was having with the electronics. Luis works as an apprentice electrician under his father, and his knowledge of electrical circuits helped greatly. We met bi-weekly to discuss the project. And that's everything for today. Thank you for watching.